Okay, so we're starting by graphing an ellipse, and then we're going to graph a hyperbola. All right, so here's the x-intercepts plus or minus 2. And we said that this is a vertical ellipse because the larger number is under y. For the y-intercepts, just set x equal to 0, and we get y squared equals 16. So for the y-intercepts, we get y squared equals 16, or y is plus or minus 4. All right, so we see it's vertical. So that's our ellipse. And we recognize this form with a minus in between is a hyperbola. And this time, if determining whether or not it's horizontal or vertical hyperbola, it depends on which comes first. All right, so in the subtraction, since x first, that means horizontal. All right, so we have some, when we set y equal to 0, we have some x-intercepts. Set y equal to 0, and we have x squared over 9 equal 1, or x squared equal 9, x equal plus minus 3. Three minus 3. And we don't have any y-intercepts. If we set x equal to 0, we get y squared equal negative 25. All right, so we can't take the square root of both sides. So we don't have y-intercepts, which is what we expected because, like we said, this is a horizontal ellipse. So it's going to go like this here and this here. All right, and what we do is draw this little box in order to do an accurate graph. We're going to draw a box that has sides, vertical sides at 3 and minus 3, and the horizontal sides will be at, that is determined by this number 25, by the square root of 25, 5 and minus 5. So let's say this is 5, and this is minus 5. For guidelines for drawing our ellipse, we draw this little box. And what we really need are the diagonals of this box. We'll extend those diagonals because our horizontal ellipse is going to have these asymptotes. Right. These dotted lines will be what they call like diagonal asymptotes for this ellipse. If we set, what is this, the equation of this line? This line has height, has slope, which is 5, height 5 over width 3. So this is y equal 5 over 3. That's one of the asymptotes. So we draw the hyperbola so that in this corner, and it starts at the ends, it starts sort of straightening out towards these lines, these dotted lines. Right. We could sort of see why it makes sense that this equation, that y, from this equation, we could see why it makes sense that y tends to, sorry, this is 5 over 3x. And this line over here is minus 5 over 3x. If we just look at this equation and we say as x, y go to infinity, then this equation okay, these terms get big, this gets big and this gets large. So they dominate and one becomes less significant. So this thing tends to it's going to be similar to, let's say, similar to this, because the 1 is going to be insignificant compared to the x squared and the y squared. Those are getting large, and the 1 is insignificant. So, and when we solve this, we have x squared over 9 is equal to, oh, let me just bring the 9 to the other side. And let me solve for y. That would be better. Okay. All right, solving for y, we have y squared is equal to 25 over 9 x squared, and square root both sides, and we have y equal plus or minus 5/3 x. So you see where that, this is called an oblique asymptote, oblique meaning not horizontal or vertical. So you see where that comes from. All right, it comes from looking at this equation. This is an approximate way of seeing that. If you look at this equation, you say when x and y go to infinity, the 1 is insignificant. So really this, it's very similar to, it tends to this equation, which is these two lines. All right. Now let's go to a 3D graph. So the first 3D graph we looked at was a cylinder. And so let's graph this cylinder. Cylinder is basically generated by, in fact, it has what's called a generating curve. It's generated by a curve in one of the planes. It always is missing a variable. So this one's missing y. Okay, so since y is missing, it's going to run along the y-axis. Okay, so it's y missing. So running along means the lines that we call the rulings. Okay, let me get rid of that t. And I'll show you what the rulings are in a second. The rulings are parallel to the y-axis. All right, so here's x, y, z. And let's just graph z equal x squared is a parabola. All right, it's along the plane that's sort of sticking straight out of the blackboard. All right, and so here it looks like this, z equal x squared. We'll see, it's going to be parallel to the y-axis. All right, I'll show you in a minute. Let's graph z equal x squared, and we have this parabola. So here's part of it we can see, we can visualize, is in our visible part, and then part of it goes behind the YZ plane. The YZ plane coincides with the whiteboard, with our whiteboard. Okay. So this is the curve z equal x squared, and then to get the cylinder, we just here, well, let me show you. Let me finish drawing this. To get the cylinder, we just extend this way. Okay, I'll draw another parabola. That's sort of the back of it. Okay, it looks a little better now. All right, I'll draw a piece of it. It's sort of like we saw one like this last time. It's like a piece of paper that's bent, not creased, but just bent, like a bent piece of paper or metal. Goes like that. Okay, it keeps extending. Extends like this behind our line of sight. Sort of like a bent piece of paper. Here are shade lines at the bottom where it's bent. Okay, so that's what this looks like. The rulings go in the direction of the y-axis. Here's the y-axis. So this line, if I draw this line, that would be a ruling. All right, so they're parallel to the missing variable, and they go along the length of the cylinder. So that would be that cylinder, z equal x squared. Okay. All right, I want to look at just, well, first we're going to look now at something called quadric surfaces. We saw a couple last time. A cylinder is not a quadric surface. Let me just show you what a quadric surface is. All right. A sphere is, a quadric surface is. They're going to take a certain form. Okay, shift, yeah, right. You shift z equal x squared along the y-axis. Exactly. Okay, so in the comment it says, so shifting z equal x squared along the y-axis, you generate a cylinder. Exactly. That's what you do. You take this curve, z equal x squared, and move it back and forth. Just move it back and forth, and that generates the cylinder. Exactly. Okay, so quadric surfaces are of this form. Quadric meaning degree 2, all right? The variables, you have some degree 2 variables. They could be that form, or you could have ax squared plus by squared plus cz equals 0. So these are quadric surfaces. These are centered near 0, 0, so, and those are the ones we're going to look at. We're not going to look at ones that are translated away from 0, 0, because then we would have many, many, many more terms. Okay, so we're only going to look at quadric surfaces of this or this form. And what we're going to do is we use traces. C, no, C's, A, B, and C are just, oh, over here? Right, no, that's CZ. Right, this one's just CZ. We could also have one that say, we could replace this with other variables, like maybe this one would be x squared, z squared, and then a y over here without squaring the y. We could have one like that too, but we're only going to, but that's sort of redundant, so we're just considering z naught squared. All right, so we're looking at ones of this form and this form. Okay, here's z naught squared over here. Okay. And the way we're going to understand the shape of the quadric surfaces is we're going to use traces to understand the shape. Okay, so traces, that means the curve formed by the intersecting the shape in one of the planes. It could be the XY plane, that would be one trace, or any of the others as well, XZ plane. And the other one would be the YZ plane. Or any, really any horizontal or vertical plane. All right. Such as, let me just say such as, the horizontal, let's talk about horizontal planes. Like z equal 1 is a horizontal plane. It's just z level 1 means height 1. So it looks like the xy plane lifted 1 unit. Okay, like z equal 1, or let's say, let me do x. Or let's say x equal 2. Okay, that's going to be a plane that's parallel to the YZ plane. okay, and it's 2 units along the x-axis. Okay, so this is how these x equal constant, y equal constant, or z equal constant, those represent planes. Like x equal 2 is a plane that's perpendicular to the x-axis. You can think of it like that. Z equal 1 is a plane that's perpendicular to the z-axis. So usually we look at traces in the coordinate planes. But sometimes we move off the coordinate planes and we look at traces in other planes as well. So that's what we're going to do to understand the shape. We're going to look at traces. So let's start with an example, and then we'll look at what these quadratic surfaces look like in general. I'll show you. We have it's in your textbook, and I also put it up. I put up a handout on MathBreeze, so we'll see what they look like in general. Okay. They're just a few different types, so we'll see what all the different types are. So here's one. Let's look at this one. X squared plus y squared over 9 plus z squared over 4 equal 1. All right. Let's say instead of 9 and 4, we had 1 here. Let's say it was x squared plus y squared plus z squared equal 1. What's that shape? We saw that last time. Okay, let's say the 9 and the 4 weren't here. Just x squared plus y squared plus z squared equal 1. Can anyone tell me what that would be? Maybe we'll do that one first just quickly, because we did that one last time. Right, exactly. That's a sphere. So this one's a sphere. I'll just draw it quickly on the side. This is a sphere. Radius 1. And it's centered at 0, 0. 0, 0, 0, I should say. Because you can think of it as x squared, y squared, z squared. They're all weighed the same coefficient 1. So you have a symmetric type of shape. So it's just a sphere. Here's the trace in the x, y plane. See, that's what I'm drawing first. The trace in the x, y plane. It's radius 1. And all over the same trace. The trace in the xz plane comes like this. And that's enough to give us the shape. I won't draw anymore. I won't draw the trace in the zy plane. Also, just if you want, we can draw that. Just another circle radius 1. All these are circle. All the traces are circle radius 1. And we just get a sphere. Okay. So that's our sphere. All right, let's now change the coefficients a little bit. All right, so we have x squared plus y squared over 9 plus z squared over 4. Anyone want to guess what shape this is? How does this affect the shape? Putting different values under y squared and z squared and x squared having different values. It's going to be similar to a sphere, but it's going to be like stretched out in one direction or the other. So it's going to be what we call, like a 3D oval, exactly. So instead of oval, we use the word ellipse. And so in 3D, the equivalent of ellipse is ellipsoid. Basically a football. Okay. And we get sort of a more accurate picture by just looking at how it looks in the various planes. You just set one of the variables equal to 0. So let's start with the xy plane. And what we'll do is we'll list xy plane. And here we list trace. XY plane just set z equal to 0. And here we have this. And then we'll write it's an ellipse. We recognize that form as an ellipse. Okay. X-intercepts will be 1 minus 1. You see, just set this equal to 0. X-intercepts are 1 and minus 1. And setting x equal to 0, the y-intercepts are 3 and minus 3. So let's go out to 3. There's minus 3 and 3. And 1 and minus 1, so it's like an ellipse like this, longer in the y direction than the x direction. All right, so that's the xy plane. Maybe next we'll look at the xz plane. All right, or maybe look at the yz plane. That's the one that coincides with the whiteboard. So let's look at the yz plane. Coincides with the whiteboard. All right, just set this equal to 0. Okay, yz plane. So just leave out, leave out x. Okay. Again, another ellipse. The y-intercepts are 3 and minus 3, same as here. Okay. The x-intercepts 2 and minus 2. And I think that's enough. We don't have to graph anymore. We get the picture, you see? That's the trace right there. Another ellipse. That's 2. And then minus 2 goes down here. Okay. So we get the picture. Basically a football on its side. So you see how we understand the shape just from the traces. That's what we do. Now, we should be familiar with the different types of quadric surfaces, like the different possibilities. Otherwise, it's not so easy sometimes to understand the shape. All right, let's do this one. We did one like this last time. Last time we did z equal x squared plus y squared. The reason why I wanted to do this one is because this time it will be nice to see traces not only in the coordinate planes, but also in the planes like z equal 4, for example, planes that are parallel to the xy plane. So the plane, let's look at these coordinates. Let's say the plane z equal 2 will be at level 2 and will be parallel to the xy plane. So it's sort of a flat plane, horizontal flat plane coming at level 2, at z level 2. So that's the plane z equal 2. And we can see traces in those as well. Sometimes it's convenient. So let's look at this one. All right. So let's talk about traces. Let me draw the coordinate, the axes. Okay. So first of all, xy plane. If we set z equal to 0, this is what we have. The only way this can be 0 is if x and y are both 0. So basically, x, y, and z are all 0. It's just a point. Not only that, we realize that z is positive because z is equal to something squared, x squared plus y squared. It has to be greater than or equal to 0. So it's only at the top half. So I won't draw the bottom half of the z-axis. Only draw the top above the xy plane. All right. Okay, what are the traces? Well, okay, let's look at the xz trace. Or let's look at first the whiteboard, yz trace, yz plane. So set x equal to 0, and here's what we get. What is this? What kind of curve is that? All right, or just write instead maybe, well, no, that's fine, z equal y squared over 4. What type of curve is this? what's that called? Just put the coefficient in front. Maybe I'll write it as 1/4 y squared. If I didn't have the 1/4 in front, z equal y squared, what shape would that be? Just forget the 1/4, just, right, parabola, exactly. So 1/4 y squared is also a parabola. It's a little bit more spread out than z equal y squared. All right, but it's just a parabola. I'm not going to draw it exactly, but I'm just going to draw a parabola here. Maybe I'll draw it a little bit spread out. All right, like that. Not as pointed as z equal y squared. Okay, I drew it a little bit spread out. So that's our trace in the YZ plane. Okay. All right, let's look at the trace in the XZ plane. Okay, so we're going to set for the, so, 1 second, I wrote XY, I meant to write XZ. Okay. Set Y equal to 0, and we have Z equal X squared. Another parabola, let me write parabola here. Another parabola. Okay, this one's a little tighter, but it's hard to draw it exactly, but it's another parabola right here. And then it sort of goes behind like that. All right, and now for this particular one, it will be convenient to see traces in planes that, what happens if we slice this horizontally, whatever this is. I want to know the trace when we slice horizontally. So in this case, it'll be convenient to see traces in planes that are parallel to the XY plane, a little bit above the XY plane. So let's look at, for example, let's look at Z equal 1. Height 1. Let's say that's height 1. Slice it like this. And what do we get? All right, so I'm just going to put a 1 here. Okay, that's an ellipse. Okay, so it's an ellipse, and the y-intercepts are 2 minus 2, and the x are 1 minus 1, but it's an ellipse a little spread out. Remember, this one was wider, was a little bit wide, and we're going to have a wide ellipse here. So, and it continues like this. You have ellipses. And now we can see the shape, right? It looks like a bowl. Not a round bowl, but a bowl. When you slice the bowl horizontally, you get ovals or ellipses. All right, so that's enough for our graph. This one's called a paraboloid because of that. It's actually an elliptic paraboloid. Okay, now here's one that we haven't seen yet. But we'll get familiar with this quadric curve. Okay. And let's look at the traces, and we'll try to figure out what this looks like from the traces. Okay, so here's x, y, z. All right. Okay, so first xy plane. We set z equal to 0. Okay. And we get y squared equal x squared. Set z equal to 0, and we have y squared equal to x squared. Or y equal plus or minus x. Two lines, all right? So we have these two lines, so the crossing. All right, it's not so, it'll get confusing just putting these in our diagram, but so I'm going to erase them. I'll keep it here, but it doesn't really help much with the curve, so I'm going to erase them. It doesn't help us visualize the curve. All right, so let's go on to the YZ plane. That's the one that coincides with the whiteboard. All right, and for the YZ plane, we put x equal to 0, so we have z equal y squared. So that's a parabola. This one's lines. Okay, so this is the parabola z equal y squared, just a parabola like this. Okay, so that's z equal y squared. And let's see, now let's look at the XZ plane, the one that sticks out of the blackboard, vertically sticking out of the blackboard. And we get z equal minus x squared. Again, a parabola, but facing down. I'll go like this because it's a parabola facing down. So it goes like this. Like I said, this one's a little hard to visualize, but I have a way to help you visualize this. But it goes like this. It goes down into the blackboard here. Okay. All right. Now let's say we get traces. Let's do traces. All right. Well, maybe I'd like to do traces that are parallel to the XZ plane. All right, parallel to the XZ plane, that means make y equal to something. All right, so let's say we have, just leave out y, and that'll be something parallel to the XZ plane. Sorry, leave out x and z, and we have y equal to a number that's parallel to the XZ plane. All right, so we have this down-facing parabola that's in the XZ plane, and I want to show that if we, that basically we're going to have parabolas all along this. So the hanging off of, you see this parabola? We're going to have parabolas sort of hanging off of this one. All right, so let's take one of them. Let me just think what I should make y equal to. Something, we'll do something positive. Let's make y equal to, let's say 4. Okay. Then we have z equal to 16 minus x squared. All right. Or let's write z equal to minus x squared plus 16. That's parabola facing down, lifted up 16. That's what it is. So here's a parabola for y equal 4. Let's say this is 4 right here. This parabola should be up at 16. Okay, it doesn't look like 16, but that's what it is. Parabola facing down, up at 16, height 16. So here, this is called a hyperbolic paraboloid, and I'll give you a way of picturing it. It's a little hard to picture now. But think of it like this, all right? You don't have to draw this, but let's say you had just a horizontal line. Think of it as a clothing line, clothesline, where you hang out clothing to dry, and you're hanging these down-facing parabolas all along it. That kind of looks like our cylinder, right? If we think of it like that, if we start like that. And now what I want you to do is just take this line and stretch it. All right, let's say the clothing line gets a little bit loose, it's not stretched so tightly, then it's going to go like this, and that'll give us, let's say you stretch this line out, that's our clothing line now. okay, and draw the parabolas hanging off of it. That's our hyperbolic paraboloid. We have to understand why the word hyperbola is in there. So far, it just looks like parabola, parabola, right? Parabola and more parabolas. What is the why is it called hyperbolic? Where does the where does that come in? The hyperbola. Okay, so do you understand what it looks like now? Okay, that's what the shape looks like. Sometimes it's called a saddle because it's shaped like a horse's saddle. All right, these of course are all connected. Those are the shade lines, like a horse's back or a horse's saddle. Okay, so you understand that, right? Yes, if you understand that. I just want to make sure you understand what the shape looks like. Okay. Okay, now what we want to do, I want you to understand where the word hyperbola comes in. So, okay, good. I'm glad you understand what it looks like. So now I want you to understand where the word hyperbola comes in, because this is called a hyperbolic paraboloid. Let me write down the name here. Okay, so I want you to understand where this hyperbola comes in. We see a lot of parabolas, but so far I don't see any hyperbolas. So where does hyperbola come in? Hyperbola comes in from slicing it horizontally. Picture if we sliced it like this with a horizontal plane, okay, a 3D horizontal plane, then you would have one intersection here cutting off that tip, and here this tip would be cut off with that curve. You see this? And that's your hyperbola. This curve here together with this curve here, cutting it horizontally. That's your hyperbola. All right, so that's a horizontal trace. Now what we have to do is, if we have a horizontal cut at the XY plane, we saw that we just get two lines. So just go up a little bit and cut here. Okay, so we want to cut here, let's say. All right, so let's say we cut, let's say at z equals 4. So here's what we have at z equals 4. In this example, we have 4 equal y squared minus x squared. Divide both sides by 4. And that's your hyperbola. All right, it's a hyperbola that is what we call vertical, meaning you have intercepts along y, and those hugging the y-axis. Let's put it that way. So if we slice it like this, we get a hyperbola. Let's make this 4 instead of 16, maybe. If we think of slicing it like this, we're going to get a hyperbola here and here. All right, it sort of hugs the y-axis. It goes around this piece of the y-axis and this piece of the y-axis. That's what we called in the two-dimensional plane. We called it a vertical hyperbola. But you see, we have a hyperbola. If we slice it horizontally, we get a hyperbola. Does everyone see that from this picture, maybe? Okay, so that's why it's called a hyperbolic paraboloid. You have a bunch of parabolas, but you also have a hyperbola. So slicing it like this gives a hyperbola, and other slices will give you parabolas. All right, so I like the word saddle for this shape because it really does look like a horse's saddle. There are two other kinds of curves, kinds of quadric surfaces. All right, so let's look at another example of a quadric surface, and then we'll look at a table. We have a table with the general form for these quadric surfaces. Okay, so there's one. Again, we understand what it looks like from traces. All right. I'll start with traces in the xy plane. Set z equal to 0, and we have x squared plus y squared equal 1, circle. So in the xy plane, we have this circle. Circle radius 1. All right, so just draw that. Okay. Let's say we slice it a little bit above. Let's say we put z equal to something else. Let's say we have z equal 5. All right, let's see what, oh, let's do 4. Z equal 4. Okay. And then we have x squared plus y squared minus 16 equal 1, or x squared plus y squared equals 17. So we have a circle radius square root 17, close to 4. So here we put z equal to 4. Let's say 4 is up here. And we have a circle radius 4. I'm going to draw it a little bit, a wider circle, basically. Coming out of the blackboard, parallel to the xy plane, flat circle. All right, so that's our circle. If we slice a little higher up. And they keep getting bigger and bigger. These circles keep getting bigger, you see? Because when z gets bigger, if you increase z, your radius is going to get bigger. Did you see that? You're going to keep getting bigger and bigger circles as we go up. And the same exact thing happens as we go down. So we can pretty much see the shape just by looking at these horizontal circles. All right, but not very well. A little bit we can see the shape. Let's see how they connect. How do they connect? Do they connect in a straight line? Do they connect in a hyperbola, a parabola? Let's see how they connect. All right. So seeing how they connect, we would look at the YZ plane. Let's look at the trace in the YZ plane to see how these connect. Remember, the YZ plane coincides with the whiteboard, so that would be good to look at. Set x equal to 0, and we have a hyperbola. A hyperbola in the YZ plane. So these connect in the hyperbola. Basically, this is our hyperbola. Wait, let me just draw it a little bit better. So basically, I want to connect the furthermost points on the circle. It's not drawn very well, but anyway, that would be one hyperbola. And another hyperbola here. I'll redraw the circles. Coming down. Okay. And when you slice horizontally, you have these circles all along. Okay, so I think you can see what the shape is, right? You can see that shape? So that's what this one looks like. This one's called an elliptic hyperbola of one sheet. Okay. I just want to do the last one. It looks like the equations are similar, except on the right, here we have the 1, and here we have a -1 on the right. Okay. So let's look at the xy plane trace. Set z equal to 0, and we have x squared plus y squared equal -1. Okay, no. Nothing in the xy plane. We can't have x squared plus y squared equal to -1. These are positive. Okay. All right. Let's say z equals some constant. Okay, then we have x squared plus y squared minus c squared equal -1. Or let's bring that onto the other side. X squared plus y squared equals c squared -1. Okay, so this has to be positive. X squared plus y squared is positive. So we're only going to get solutions if this is positive. Okay, so if c squared -1 is greater than 0, then we're going to have a trace. So that is c squared greater than 1, or c greater than 1, c less than -1. So we'll have traces for those values, and we'll have circles. This is a circle. In these cases, we're going to get a circle. So horizontal planes are going to cut this thing in a circle. But there's nothing between 1 and -1. No circles between 1 and -1. And we have a bunch of circles above 1 and below -1. All right? Just from that alone, we can picture what this looks like, just from this information alone. Let's do one other thing, though, one other trace. Let's look at the whiteboard. And the whiteboard is the YZ plane. Let's look at the YZ plane. Put x equal to 0, and we have y squared minus z squared equal -1. We're multiplying both sides by -1. We have z squared minus y squared equal 1. So this is a typical hyperbola. All right, now we're ready to graph this. And if you're familiar with the shapes, it's easier to graph. Like if you've never seen these shapes, then it's more complicated. But if you more or less know where you're heading, it's easier to graph. What you're going to have to do is not actually graph, but pick out the right picture. Like, does this equation correspond to this picture? You have a problem like that in the homework, and we'll do a problem like that in class. All right, I think next time we'll do that problem in class where we match an equation with a picture. That's what we're going to do. All right, so anyway, let's do this hyperbola. Z squared minus y squared equal 1. That's in this whiteboard, the plane corresponding to the whiteboard. So here we're going to have some z intercepts at 1 and -1. No y intercepts. And here we draw a hyperbola in this whiteboard with the z-intercept. So it's going to hug the z-axis. The hyperbola is hugging the z-axis. Oops, I should draw these both dotted. Okay, so that's my hyperbola, facing up, facing down. And horizontal slices give me circles. That's what we said. Nothing in between here and here. But these horizontal slices give me circles. All these. That's what we said from here. X squared plus y squared equal to a positive number is going to give us a circle. X squared plus y squared equal to a negative number gives us nothing. You see, that's the nothing. All these slices are circles, so let's just draw some circles. So basically we have like a bowl facing up and a bowl facing down. That's the last type of quadric surface that we're going to look at. Okay, so that's the last one. So let me just show you. We're going to Math Breeze now. In section 144, I just have a little chart of various quadric surfaces, the ones that we covered. So let's go to Math Breeze. I'm just going to go there for a second. Okay, let's look at 144. One thing I want to show you in here. Okay, so here in 144 we have something, you can think of it like a handout or some notes on table of quadric surfaces. So let's look at that table. And here you see different equations and what they look like. All right, equation of this form, we saw that ellipsoid. We saw something like this, one bowl sticking up. This is that saddle, like a horse's saddle. Okay, so this is a general form of the equation. And a couple more. Okay, and then we had this shape, and this is called elliptic hyperboloid. And this last one that we did that looked like a bowl facing up and a bowl facing down. That one had the -1 on the right. It's called, again, elliptic hyperboloid of two sheets, like because they're separate, two separate ones. All right. This one, what does that shape remind you of? I've seen things like that. I think maybe containers, large containers that contain oil, sometimes are shaped like that. You see those near the airport. Okay, so I want to show you that. And next time I think we'll do a problem that we have in the back of the book that's similar to what you do in the homework. So here in the textbook exercises 144, I'm just clicking on that in MathBreeze. All right, let's go down to 144. I'm going to scroll down to that. And I'll just show you the problem we're going to do next time. Here it is. Okay, this is from 144. Basically, we're going to match the equation with the graph. Here we have some graphs and match the equation with the right graph. And you have one like that in the homework too. So I think next time we'll do this example. And that'll finish 144. Okay, any questions? No? Okay. All right. Okay, so enjoy your weekend. Okay, I think you have homework 143 due. All right, I think maybe tonight. I'm not sure. Just look it up on MathBreeze. But enjoy your weekend, and we'll see you Monday. Okay, take care.